Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So we started this fundamental concepts in organic chemistry or organic reaction mechanism in our last class. So initially we studied about substrate or maybe an organic molecule is there and when organic molecule reacts with a reagent or the attacking species. It forms an intermediate and intermediate on further conversion converts into the product or maybe the byproducts. So this is what the organic molecule which provides carbon to a new chemical bond is called substrate and these are usually organic molecules and attacking reagent. The reagents are usually inorganic molecules and they provide heteroatoms usually and maybe they help in the carbon carbon or other bond formation. So they help the reaction to proceed in the forward direction in many ways, but usually they do not provide carbon atom to the new bond until unless both the molecules which are taking part into the reaction, both the reactants taking part into the reaction, they form carbon-carbon bond. Then in that case, one is considered as a substrate arbitrarily and another is considered as a reagent. So the substrate and these things we have already seen the reaction mechanism. Then we start this term reaction mechanism. I have explained, and this reaction mechanism is if a reaction is happening, you are starting with certain reactants, and those reactants then converts into the product, final product, and this conversion into the final product may happen different steps. And so in that case, reaction is a multi-step reaction or complex reaction, you can say, or maybe whether this reaction is happening in only one step in the concerted way, non-concerted. There are many terms in what way the reaction, these reactions are converted into the product. The entire energy profile, this entire profiling, this energy barrier and the thermodynamics, everything is associated with the reaction mechanism. So reaction mechanism includes thermodynamics. Thermodynamics means the relative stability of product and reactant or intermediate with respect to the reactant, and the kinetics means the each associated barrier of each step of the reaction. Then we have seen the fusion of a covalent bond. We have seen usually the chemistry or organic chemistry what we see old bonds break and new bonds form. So breaking of the old bonds is called cleavage of the bond or the fusion of the bond. In organic reactions, there are two types of fusion that happens: the heterolytic fusion or heterolytic cleavage or and homolytic cleavage. Heterolytic cleavage means the electron shared pair of electrons goes both the electrons of the shared pair goes to a particular atom and another atom which acquires positive charge. So the one which accepts both the electrons acquires positive charge. So in heterolytic cleavage, we see the formation of two charged species. So these two charged species forms and if and in the heterolytic cleavage and if these the positive charge in out of this charge species which are being formed, if the positive charge is over the carbon atom, then such a species is called carbocation, and the carbocation stability of carbocations we have also seen. The tertiary carbocation is most stable, then the secondary carbocation, then the primary, and then methyl carbocation. This is methyl carbocation, and the shape of carbocations we have also seen, and some other properties like substate of electron and other things. sp2 hybridization of the carbon which carry positive charge and so on. These things we have already seen. What else we have seen that in the heterolytic cleavage, the bond, the fusion of bond is shown with the curved arrow, and the shared pair of electrons we show that we start this arrow at from the middle of the bond to represent that the shared pair of electron goes to the another atom, and the atom at which this electron goes in the cleavage is at that atom this arrow ends. So this arrow starts with the middle of the bond and ends at the atom which accepts shared pair of electrons. And which atom will accept shared pair of electrons? We have seen the atom which is higher in electronegativity usually accepts the shared pair of electrons. And what are the conditions which helps in heterolytic cleavage? So we have seen heterolytic cleavage after heterolytic cleavage. Charged species are formed and charged species are more stable in polar solvent. So polar solvent will help heterolytic cleavage. And also there are conditions which help homolytic cleavage. If those conditions are not there, then the heterolytic cleavage will be favored, like presence of peroxide. whether it's the peroxide, alkyl peroxide or hydrogen peroxide, because these peroxides have very strong tendency to form radicals because OO bond is not a strong bond, and we see RO bond. So RO, two RO groups are connected through oxygen atoms, and these oxygen atoms, both the oxygen atoms had two lone pairs. And these two lone pairs, they're continuously repel to each other. So these bonds, oxygen single bonds are not stable, so they have tendency to break from that place. O bond, and so it will form radical because both the atoms have same electronegativity, and so these atoms will take one electron from the shared pair, means they'll take their own electron which they have shared in the bonding, and so the two odd electron species will be found which are neutral species. Has not, it has incomplete octet, because to complete octet they have formed the bond. So since this bond has broken out and they part away with their electron, and so they are odd electron, they are having incomplete octet, they are neutral species. This is how the radicals are formed in homolytic cleavage usually. So what I was actually explaining in the homolytic cleavage, certain conditions like presence of peroxide catalyst, the presence of sunlight, presence of very high heat, these are the conditions which prefer homolytic cleavage. And so if these conditions are not there, then the heterolytic cleavage will happen also. Then we have also studied about the homolytic cleavage. Homolytic cleavage means the both the shared pair of electrons. But before I go again explain the homolytic cleavage, what we have seen that here what we have seen, the positive charge is charge appear on the carbon atom. There can be one species where the positive charge means negative charge appear on the carbon atoms. Like for suppose if I say CH3 twice Cu, CH3 twice Cu, so CH3 copper bond is there. In that case, the carbon is having more electronegativity than copper. So if the cleavage of such bonds will happen, carbon will acquire a negative charge. So if the carbon acquires a negative charge, and that also is up because of the heterolytic cleavage, carbon can also acquire a negative charge. And when carbon acquires a negative charge, so carbon ion is formed. So carbon ion means the carbon having negative charge, carbocation carbon having positive charge. Carbocations are also known as carbonium ion. So carbon ions, their shape and other things we have already seen. Here the pyramidal shape like ammonia I have explained, sp3 hybridization carbon, distorted tetrahedral like the, and what we see, the stability of carbon ion, it goes with the methyl carbon ion is most stable than primary carbon ion, then secondary carbon ion, and then the tertiary carbon ion. This is why, thus because of the same reason, this species is more stable. The region that we have looked for the stability of carbocation here, same region destabilizes carbon ion. Like what we have seen, methyl groups are electron donating groups, and they increases electron density at the carbon at which they are connected. And so the electron density is increased. It means if it is positive charge species, so that positive charge is suppressed, and the charge separation means what? Or the stability of the system will increase. Charge separation, this always increases the stability of the system until unless system is not neutral. So in the case of negative charge species like carbon ion, if this methyl group will give electron to this carbon atom, so carbon electron density of this carbon atom will further intensify, it will increase, and so the stability of the system will decrease. Another reason is not the plus R effect, that is what plus I effect, that the electron donating effect. Another reason that we cite is the no bond resonance or the hyperconjugation. And then what is no bond resonance and hyperconjugation, that we will see later on. But and you can just see that the methyl groups, when it is in conjugation with the carbocation or carbon ion, it also shows the hyperconjugation, and because of the hyperconjugation, negative charge species gets destabilized and positive charge species get stabilized. Positive charge species get stabilized because of the hyperconjugation, and negative charge species get destabilized. Please remember this. And so carbon ion becomes destable when we add methyl groups to the carbon center having negative charge, and carbon cations get stabilized. Just give me 1 minute. So these things we have already seen. The homolytic cleavage, the conditions I have just explained. The homolytic cleavage Now let's look at the homolytic cleavage we saw at the fish by fish hook. So two fish hooks we use, or the half curved arrow, half headed arrow, curved arrow, and they form free radicals. You see here these two half hooks, one in this direction, one in this direction. It originates at the center of the bond, covalent bond, and each half hooks ends at the bonded atom. And so this heat or presence of light, it facilitates the homolytic cleavage. The presence of high heat or light facilitates homolytic cleavage, or the presence of peroxide catalyst, or presence of non-polar solvent, they all facilitate homolytic cleavage. And we have seen the homolytic cleavage, it forms the free radicals, and the free radicals odd electron species having one electron deficiency from their octet. So they are called free radicals, and if these free radicals are on the carbon, so what electrons are on carbon, so they can be primary, secondary, or tertiary, or methyl free radicals. And we have seen the order of the stability of free radicals, alkyl free radicals, are the same as we have seen for the carbocations, and the reason is the same. Because of the same reason, free radicals are stable, and the stability of the free radicals follow this order. And what is tertiary, secondary, primary carbocation or free radical or carbon ions? This I have explained. The carbon atom is associated to one alkyl group, the primary, like this. If this carbon atom associated to two alkyl groups, secondary, and if it is associated to three alkyl groups, tertiary, no alkyl groups, then methyl. This is how this term goes. Now let us see this question. Using curved arrow notation, show the formation of reactive intermediates when the following covalent bonds undergo heterolytic cleavage. So what is given? These bonds are undergoing heterolytic cleavage. The bonds are shown here, heterolytic cleavage. And we have to show the curved arrow by which, using this curved arrow notation, we have to show the formation of reactive species, and which reactive species will be formed when these bonds undergo heterolytic cleavage. So what we have to find out first is the shared pair, the bonded atoms. So here the bonded atom is carbon, and sorry, silicon, sulfur, and sulfur is bound to the carbon through a single covalent bond. When this bond will be broken, so we have to then first step is what are the bonded atoms, carbon and sulfur. Then we have to find out in the heterolytic cleavage which atom is having a higher electronegativity. So definitely sulfur has higher electronegativity is below oxygen. So its electronegativity is more than that of carbon. And so then we can understand from here that to which atom the shared pair of electron will go. And once we understand the shared pair of electrons, we will just have to show the curved arrow. So this shared pair of electron will go on sulfur atom since its electronegativity is more than that of the bonded carbon. And so one can use this arrow as you can see here in this example. And this arrow, once this bond is broken, after breaking of this bond, a carbocation, methyl carbocation, and this charged species will be formed. It is thiol, so you can say thioxide. So this is the species that is formed, and this is carbocation. So these are two intermediate species that will be formed because of the heterolytic cleavage of this bond. Now the next is question, CH3CN. Here what are the bonded species? Carbon and this carbon. So both are carbon. But what do we see here? This carbon is bonded with this nitrogen through a triple covalent bond, and this triple covalent bond, and this carbon is broken to the, it's linked to this nitrogen atom through a triple bond. So this association is very strong. So this CN bond is not going to be broken because breaking triple bond is very difficult, as you know. So this bond, this CN species, anyway we have to break this bond. This breaking of this bond is not asked in this question, but even if it is not asked, you should understand this carbon and nitrogen having triple bond, so they will be together always. And so if this bond has to be broken, so this bond, now the CN species you have to consider. So this is not C, this is CN, and the nitrogen is having higher electronegativity, so nitrogen pulls away electron density from carbon, and three bonds are there, so it actually pulls three electrons of carbon towards itself. So this carbon will be having very high very low electron density. So it will be having at least 3 delta plus charge. And once it acquires a delta plus charge, its electronegativity will increase. So any species which is having a positive charge, its electronegativity will increase because the one electron which was actually shielding the effect of the nucleus is now unavailable. So by that much amount, effective nuclear charge will increase. So anyway, so the effective nuclear charge of this carbon will increase, so its electronegativity is increased. And once its electronegativity is increased, so you can consider this entire CN group as electron withdrawing group or the more electronegative group. And so the electron now will move to this CN group or the carbon atom. And so because this carbon atom is having higher electronegativity because of its associated nitrogen, so we have to show the curved arrow in this way, which ends at this carbon, which accepts the electron, shared pair electron. And so this curved arrow is shown in this fashion. And again, the methyl carbocation will be formed and the cyanide anion will be formed. Now the next example is CH3Cu. CH3Cu, and in this case this is copper, and copper is a metal, and we know all the metals have lower electronegativity than the carbon because metals are usually electropositive, they are not electronegative, and carbon is a non-metal. So copper will be having lower electronegativity than the carbon, and so if this bond has to be broken electrolytically, carbon will accept the shared pair of electrons. And because even in this bond, carbon has pulled this electron, even when this bond was intact, the shared pair of electron towards itself because of its higher electronegativity. So we have to show this arrow in this fashion. So carbon, the shared pair of electron will go to this carbon, and this arrow will start at the middle of this bond as shown here. So this shared pair of electron will go to this carbon, and this copper will acquire a positive charge after the electrolytic cleavage, and this will form a negative species. Negatively charged carbon species will be formed, which is a carbanion. This is methyl carbanion because this is a methyl group. And we know this is a trigonal planar structure, this is a pyramidal structure, this carbon is sp2 hybridized, this carbon is sp3 hybridized, and so on. Many other properties we know. Let us now again see the substrate and reagent. These terms again in more details with certain examples. So a molecule whose carbon is involved in a new bond formation is termed a substrate. So molecule which again I'll just read because these things I have already explained. So a molecule whose carbon is involved in a new bond formation is termed substrate. Thus, the substrate is a substance that undergoes a chemical transformation. The substrate is also a substance that undergoes a chemical transformation, and in that chemical transformation, it provides its carbon to form a new bond. The inorganic compounds that bring about the organic reactions are called reagents. So usually inorganic compounds that bring about these organic reactions are called reagents. For example, in this case, like this is an ethylene molecule, and ethylene molecule, this bromine is undergoing addition. So bromine is undergoing addition on this ethylene molecule. So these two bromine atoms are there. This is Br2. So one bromine goes to this carbon, another bromine goes to this carbon, and this double bond will become a single bond. And in this case, what do we know? This bromine is a inorganic molecule, and this is an organic molecule. And this organic molecule now, then this inorganic molecule is what it is called a reagent. This is a reagent. This is product, and this is a substrate because the new bond, anyway new bond is formed. This C and Br bond is a new bond. Carbon bromine bond is formed here, and here also carbon bromine bond is formed. And this new bond, this substrate, this reactant is providing carbon to a new bond. So this is a substrate. So new bond, carbon bromine bond. In this carbon bromine bond, carbon is provided by this molecule, and so this is a substrate, ethylene molecule, and the bromine, the other molecule which is a reagent, which is called reagent, and this is also an inorganic molecule, which means reagents are usually inorganic molecules. Other than few cases, and when a carbon-carbon bond is formed, naming the reactant as a substrate and reagent is arbitrary choice. So when the carbon-carbon bond is formed, so naming which one is a reactant and which one is a substrate or which one is reagent is arbitrary choice, and based on that, and mostly we'll look at the at what atom we are focusing on, we can call it that as a substrate. And usually the organic compound which has more number of carbon atoms, usually we consider them as a substrate. For example, if you look at this reaction, this is a benzene molecule and this is chloroform, both having carbon atoms, and this carbon-carbon bond formation happens here. You see, this is the toluene molecule. The product is toluene, and in this toluene, we see this substance, this carbon-carbon number of carbon atoms is usually more in benzene. So we consider this as a substrate and this one as a reagent. However, both the reactants are providing carbon to this new bond. A new bond between this carbon and this carbon is being formed here. And both this reactant and these reactants are providing carbon to this bond. So the choice could be arbitrary. However, you may be biased towards the substance or towards the molecule which is having more number of carbon, and you can consider them as a substrate. So this will one can say this as a substrate and this is a reagent, and anyway this reagent is now converted into HCl, and so this is the product. And this is the carbon species which contains the carbon and new bond is formed is called the product. This is also a product, but this is the main product of this reaction. Let us now try to understand the another two terms, the nucleophile and electrophile. These are also very useful terms and very important terms. Without understanding the meaning of these terms and their examples, you will not be able to understand organic chemistry. So please pay attention here. So, nucleophile, as you see this name, if you understand the meaning of this term itself, nucleophile, philes means the lover, and nucleo means the positive charge. Nucleus is positively charged; it contains electrons. So, anything which is positive charge loving or the positive center loving is called nucleophile. And which chemical species will be positive charge loving or the nucleus loving? The one which is electron deficient. No, sorry, one which is electron rich. The species which is already electron rich, that will be attracted towards a positive charge center. And so the nucleophiles are what? Nucleophiles are electron rich species. These species may be having a negative charge. So if it is having negative charge, so it will be attracted towards a positive charge hole or positive center or a positive charge species. And or what else it could be, the electron rich species other than the negative charge means the species having a lone pair of electrons, and this lone pair of electrons can also be available and can take part in a chemical reaction. So the species having lone pair of electrons also behave as a nucleophile. Another species which can behave as a nucleophile is the pi electron species, like species which are having very high pi electron, very large pi electron cloud or very high pi electron density, then such species are also species also behave as nucleophile. And then the counter term is the electrophiles. The species which are attracted towards the electron is the negative charge, and negatively charged philes means lovers. The species which are electron lovers or negative charge lovers are electrophiles, and these species will be electron deficient species. Anyway, so the electron deficient species will be electrophiles. And what are the electron deficient species? The species which are having positive charge. One thing, if it is having positive charge, so it will definitely be attracted towards the electron rich species or the electron rich species. So the positive charge species are electrophile. Another species which is the species which for some of the atom, for one of the atom, the octet is not complete. So incomplete species with having atoms with incomplete octet are also they also behave as electrophiles. So octet is not complete, or maybe species which are having tendency to accept electrons like Lewis species, like metal ions. So metals are the cations, metal cations. So they have vacant orbitals. So species which are having vacant orbitals, they also behave as electrophiles. So how will you identify electrophiles? Positive charge will tell if the positive charge is there, species is electrophile. If the species is having incomplete octet, species is electrophile. If the species is having a vacant orbital, whether the vacant p orbital or vacant d orbital, if it is having a vacant orbital, means it is an electrophile. It is electron deficient species. So electrophiles are electron deficient species. Nucleophiles are electron rich species. So if the attacking, let us now see the reagents attack the reactive species, reactive sites of the substrate. The reactive site may be an electron deficient portion of the molecule. That's an example, an atom with an incomplete electron shell. Let us now get acquainted with two more terms, nucleophiles and electrophiles. Similarly, we'll see more terms, nucleophilic attack, electrophilic attack. Nucleophilic centers and electrophilic centers. So just first understand what is a nucleophile and what is an electrophile. So nucleophiles are usually electron-rich species, and electron-rich species means this species can have lone pair of electrons. They may carry even negative charge, or they may have pi electron cloud with them. So nucleophiles are usually electron-rich species, and the word nucleophiles itself means someone is having affinity with the nucleus or the positive charge center. Nucleus means the nucleus, the sign means the loving. So nucleus loving or positive center loving, a positive center loving species will be the electron-rich species, because only electron-rich species gets attracted or nucleophilic or towards a positive charge center or the electron deficient center. And similarly, the term electrophiles means a species which has an affinity, a stronger affinity with the electron-rich species on the electrons. And electron-rich means electrophiles are electron-deficient species. So electron-deficient electrophiles are electron-deficient species. They have affinities. They want to get attracted toward the electron-rich species, which are nucleophiles. So reagents and these nucleophiles and electrophiles are usually reagents, and reagents we have already seen. Reagents is any other species which any species which do not provide carbon to a new bond or reagent. So nucleophiles and electrophiles, they can have carbon atoms as well, but mostly the nucleophiles and nucleophiles are electron-rich species having a heteroatom. But these atoms can have, these nucleophiles can have carbon center as well, because carbon ions are electron-rich species that they also have carbon. And if a carbon ion attacks a nucleophilic center, so what we see the formation of a carbon-carbon bond. But OH minus ion, SH minus ions, we'll see what are the different examples of nucleophiles as well as electrophiles. So if you know that nucleophiles, ammonia is also a nucleophile, but it has a heteroatom nitrogen uh, which lone pair gets attracted towards a positive charge center. So reagents attack the reactive site of a substrate. The reactive site may be an electron deficient portion of the molecule. The molecule can have electron density in molecules are not equally distributed, that is not isometric. And so what we see there are certain portions of the molecule has a larger electron density, and so it has a negative potential. One can understand in terms of potentials, and some portion of the molecule have lesser electron density. So electron density is depleted from that region. So we can have a positive potential in that region. So any portion of molecule which has a depleted electron density, where we can assume to have a positive potential, those centers are actually the nucleophilic centers, where nucleophile can attack, can go and combine. So the reactive sites may be electron deficient portion of a molecule, a positive reactive site. Example, an atom with an incomplete electron shell or positive end of the dipole in the molecule. If the attacking species is electron rich, it attacks these sites. So electron rich species attack these sites, electron deficient centers, which is maybe because of the incomplete octet or maybe because of some other reason. A reagent that brings an electron pair to a reactive site, such reactive sites which are electron deficient, is called nucleophile. So such a reactive site is called nucleophile. That is nucleus seeking and the reaction is then called nucleophilic reaction. If the attacking species is electron deficient, so attacking species can be electron deficient as well, because we have also, as I have said, a certain portion of the molecule can have higher electron density. And if it has a higher electron density and a sequentially a negative potential, so some electron deficient species can get to attracted towards it. So if the attacking species is electron deficient, the reactive site constitutes that part of the substrate molecule that can supply electrons. Example, pi electrons in double bond. So pi electrons in a double bond are electron rich centers, because pi electrons are loosely bound centers, and with those centers and electron deficient species can attack, because pi electron centers are easily available to any electron deficient species. So a reagent that takes away an electron pair from a reactive site is called electrophiles, and electrophiles are represented as E plus, nucleophiles are represented as Nu, and with a lone pair of electrons like this. This colon sign, it is actually, this one represents a lone pair of electrons. So Nu colon, lone pair of electrons, it represents nucleophiles. Electrophiles are denoted as E plus. E plus, it represents E. This the electrophiles, that plus represents it is an electron deficient species. The electron deficient species may not have a positive charge, but that can be represented as H plus to denote that this is electron deficient center, may not have a actual plus one positive charge. And so a reagent that takes away an electron pair from a reactive site is called electrophile, that is electron seeking. Electrophile means electron seeking, the one which requires electron, the one which wants electron, the one which loves electron, and means the negative charge, negative potential, negative ion, and the reaction is called electrophilic. And so if the electrophiles attack happens during a process, such a chemical reaction is called electrophilic chemical reaction. And if a nucleophilic attack happens in a chemical reaction, then such a reaction is called nucleophilic reaction. A nucleophilic reaction, we have just seen here. The nucleophilic attack during a chemical reaction, so reaction is called nucleophilic reaction, and this nucleophilic reaction, no nucleophilic substitution reaction are one of the example of nucleophilic reactions. Nucleophilic substitution of first order, second order, and even some other type of nucleophilic substitution reactions are also there. And so electrophilic substitution reactions are also there. Nucleophilic substitution reactions are properties of saturated molecules or carbonyl compounds, or the saturated alkyl halides give nucleophilic substitution reactions. But the electrophilic substitution reactions that we see, it is given by aromatic molecules like benzene. Benzene gives electrophilic substitution reactions very easily because it has electron density, pi electron density, which are available to electrophiles. But we also know that even though these pi electron densities are there, but these pi electrons are involved in aromaticity. So once you add the electrophiles, it will not be stable in that condition. So some of the groups depart, and that is what we call the substitution. So what are different types of chemical reactions, substitution, elimination, those things we will see later on. This is the first focus on this point. So during a polar organic reaction, a nucleophile attacks. The polar organic reaction means the polar species are involved and the solvent is a polar solvent. The polar organic reactions, we have also seen what is the polar organic reaction, means the reaction where heterolytic cleavage of a bond happens or heterolytic fusion of a bond happens. Such reactions are also called polar reactions or polar organic reaction. And in a polar organic reaction, the nucleophiles attack an electrophilic center of substrate, which is that specific atom or part of the substrate that is electron deficient. And what are the examples? We'll see, like the alkyl halides. Alkyl halide atoms are connected to certain carbon atom in that molecule, and that carbon atom has electron deficient center because this halogen atoms have very high electronegativity, and because of the high electronegativity, they will pull away electron density from the carbon center, and the carbon center becomes positively charged. It acquires certain partial positive charge, and so it becomes a nucleophilic center. So similar, so what it becomes? So during a polar organic reaction, nucleophile attack electrophilic center. Sorry, it becomes electrophilic because it wants electron. Becomes electrophilic substrate center, which is that specific part of the substrate that is electron deficient. Similarly, the electrophiles attack a nucleophilic center. So electrophiles attack nucleophilic center. Electrophiles are electron-rich species which gets attracted towards a negative charge center or electron rich center. Electrophiles are electron deficient centers and nucleophilic centers are what? This center is nucleophilic, which means it is having higher electron density, so it will be attracted towards some species which is electron deficient, so that is electrophile. So the similarly electrophiles attack at nucleophilic center, the electron rich center of the substrate. Thus, electrophiles receive an electron pair from the substrate when the two undergoes bonding interaction. So, electrophiles receive electron pair from a substrate when the electrophiles undergo bond interactions with the substrate. A curved arrow notation is used to show movement of an electron pair from the nucleophile to electrophile. So this is a common, it's a general thing in organic, not only in organic chemistry, in entire chemistry. So we show the movement of electrons pair. So from system when the electron, from where the electron pair moves, we start the arrow at that center and we end the arrow at the position where that electron pair is going. So even this kind of things we have seen earlier in the heterolytic fission. So we start the arrow from the middle of the bond to represent that this shared pair of electron is moving and we end the arrow at the atom which is accepting the electron pair in heterolytic fission. So similar thing we can also show. So we also use a curved arrow and this curved arrow we use to show that from the movement of electrons from nucleophile to the electrophile. Nucleophile means electron rich species which is having a lone pair of electrons or a negative charge or maybe pi electron cloud to the electron deficient center. The curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile, and some examples of nucleophiles are negatively charged ions. Negatively charged ions or the carbon ions are nucleophiles because they are all electron rich species, or the species, neutral species with the lone pair of electrons are electrons also behave as nucleophiles. For example, water molecule, ammonia molecules, they are also nucleophiles. Some other examples of negatively charged nucleophiles are HO minus, cyanide ions, this is hydroxide ion, cyanide ion, all the carbon ions, SH ion, SH minus ion, chloride, bromide ions, all the halide ions, they are all nucleophiles. And the neutral species are also, they may also behave as a nucleophile if they have lone pair of electrons. For example, water, ammonia, alcohols. You can have ethers as well. All the three amines, primary, secondary, and tertiary amines, are electron-rich species and they behave as nucleophiles. Like you see here, this is a tertiary amine R3N and so on. They can act as nucleophiles due to the presence of lone pair of electrons. So they all can behave as nucleophiles. We can also have nucleophiles like I have seen electron-rich species, the aromatic compounds like benzene. It has a pi electron cloud and its pi electron density can also be available to an electron deficient species. So the example, another example of nucleophile is pi electron system like aromatic molecules. The examples of electrophiles means the electron deficient species include carbocations. Electron deficient species can have a positive charge, and the positive charge is there. If the positive charge is there, it means that the species is electron deficient. The positive charge species, the intermediates, all the carbocation intermediates are positively charged species, and so they are electrophiles. There are certain neutral molecules as well, which behaves as nucleophiles if they have incomplete octet, like for example BH3. BH3 it is having sextet of electron in outermost shell. So boron has only 6 electrons in outermost shell. So it has a vacant p orbital. So if a chemical, some of the atoms of the chemical species is having an empty or vital, then that chemical species can also behave as an electrophile. There are also chemical species which do not, which have complete octet of all the atoms, all the elements that are part of that chemical species, but they still behave as electrophiles, and this electrophilic behavior is because of the polar nature of the bond. For example, if you remember the carbonyl compounds, aldehydes or ketones, we see there is a carbonyl bond, C double bond O. Because of the higher electronegativity of oxygen, we see the shifting of the two, both shared pair of electrons towards oxygen, and so the carbon center gets certain positive charge, some partial positive charge, and because of generation, the creation of a partial positive charge at the carbon center of the carbonyl group, this carbon center behaves as an electrophile. So it becomes electrophile. Similarly, other examples are alkyl halides. So alkyl halides, halides atom, chlorine, chlorine, bromine, so chloride, fluoride, bromides, their electronegativity is higher than that of the carbon, and so these chemical species, halides, can also pull away shared pair of electrons from the carbon, and so the generation of partial positive charge will happen at the carbon center, and so all the alkyl halides are the carbon center at which the halide atom is attached, they behave as electrophile. And not only the halides but also the alcohol. The center, the carbon atom at which OH group is attached, it requires certain positive charge, so that center is also behaves as an electrophile. So the carbon atom also behaves as electrophile to which the OH group hydroxyl group is attached in an alcohol. So the examples of electrophiles include carbocations and neutral molecules having functional groups like carbonyl group, C double bond O, or alkyl halides are 3CX, where X is halogen atom. The carbon atom in carbocations has a sextet configuration. So this is what we see, the carbon cation, which we already know has sextet electronic configuration, and hence it is electron deficient and can receive a pair of electrons from the nucleophile. In neutral molecules such as alkyl halides, the one example we have also seen, neutral molecules can also have a sextet of electrons or can be have an electron deficient center. For example, BH3 such molecules. So they are Lewis acids, and so all the Lewis acids can be electrophile, and there are also neutral species like alkyl halides or the carbonyl compounds that we have seen, where we see the generation of an electrophilic center due to the polarity of CX bond. A partial positive charge is generated on the carbon atom, and hence carbon atom becomes an electrophilic center at which a nucleophile can attack. Let us now see some questions giving justification. Categorize following molecules ions as nucleophiles or electrophiles. So nucleophile, the example HS minus, this HS minus, this is species having a negative charge, this is electron rich species, so it will be a nucleophile. So let us first write a nucleophile and electrophile, and we will see each species, will go at each species and we will see also whether this species is electron deficient or electron rich, and based on that we will categorize them in terms of nucleophiles and electrophiles. So HS minus is electron rich species, it is having a negative charge, so it is an nucleophile. Now BF3. BF3 is a Lewis acid, you know, and this is Lewis acid means boron has a incomplete an empty p orbital, and this is because boron has only a sextet of electrons. Boron itself has only 3 electrons in its valence shell, and 3 electrons is also obtained from 3 fluorine atoms due to sharing of electrons. So 3 plus 3 total 6 electrons are only there in its valence shell in this BF3 molecule, and so boron there is an empty p orbital at boron, so this BF3 behaves as electrophile. So this one is an electron deficient center. BF3 is an electron deficient center, so it will be an electrophile. Now C2H5O minus, ethoxide ion. This ethoxide ion is having a negative charge, so it is an electron rich species, and an electron rich species is a nucleophile, so it will be a nucleophile. So we'll put it here. Now CH3 thiophene. This is a tertiary amine. And this tertiary amine is having a lone pair of electrons at nitrogen. The lone pair of electrons are also electron rich species. So any species having a lone pair of electrons are usually they are electron rich, and such centers we have as a nucleophilic center. So this is also a nucleo. So this the centers are electrophilic centers, and this species is a nucleophile. So this is also a nucleophile, and this center is an electrophilic center because it wants to get attracted towards a electrophile electron deficient center. So it will provide its electron to an electron deficient center. So it is electrophilic center, but this species is a nucleophile. Now H2N, sorry, then the next species Cl plus. So this species is having a plus charge, positive charge, so this is an electron deficient species, so it will be an electrophile. So Cl plus is an electrophile. Then CH3C plus double bond O. Now there is a positive charge at the center, and if there is a positive charge at the center, so anywhere, so what we see this species is an electron deficient species, and so it will be an electrophile. And this center is a nucleophilic center, and it will be attracted towards a nucleophile and electron rich center. So this is electrophile. This is an electrophile. Now the next species H2N minus. So this H2N, this amide ion, this amide ion is having a negative charge as well as the nitrogen has a lone pair of electrons, and so this is an electron rich species, so it will behave as a nucleophile. Now N plus O2, N plus O2 we see in N plus O2 there is a positive charge of this nitrogen, and so there is an electron deficiency at this nitrogen. So this is an electrophilic species. So what we see, so we have segregated all the species in the form of species in nucleophiles and electrophiles, and the nucleophiles, these all of these species have one shared pair of electrons, which can be donated to an electrophile. And in this species, what do we see? The reactive sites have only 6 valence electrons, and thus they can accept electron pairs from a nucleophile. So we see at this center only 6 electrons are there. 6 electrons, because we see only 3 bonds are there to this carbon, 2 bonds with this oxygen, one bond with this carbon. So this center has only 6 electrons. This nitrogen is also having 6 electrons. Cl plus is also having only 6 electrons, and in boron atom in this BF3 molecule is also having only 6 electrons. So they are all having only 6 electrons in its valence shell. So certain centers are there which is having only 6 electrons in its valence shell, and so this are electrophiles. Another way is to understand these species are electron efficient species, and electron deficient species are also electrophiles. Let us now see another question. Identify electrophilic center in the following and the following chemical moieties. So this is CH3 CH double bond O. This is an aldehyde. We see a carbonyl bond C double bond O. Then CH3 CN is cyanide of the cyano compound, and CH3I is the alkyl halide. So what do we see? This oxygen atom is because of the high electronegativity of oxygen. We see a partial negative charge will be accumulated as the oxygen because of the shifting of electron density toward oxygen, and so the electron density will be depleted from this carbon. Electron density is depleted from this carbon. It means this carbon will acquire, it will attain certain positive charge, some partial positive charge, and because of that, this carbon will be has an electrophilic center because it will. So this is electron deficient center, so will be attracted towards the electron. And now let us see this H3C C triple bond N. Again here what do we see? We see that there is a carbon triple bond nitrogen. Nitrogen is having higher electronegativity. Because of higher electronegativity, we again see the shifting of these 3 electron pairs towards nitrogen, and so a partial positive charge will be generated at this carbon, and so this carbon becomes electron deficient, and so it becomes electrophilic center. Now this H3Ci. This iodine is having higher electronegativity than this carbon, and so again we see the shifting of the shared pair of electrons toward this iodine, and thus the partial positive charge will be generated at this carbon, and so this will also become an electrophilic center. So this will become electrophilic center, so it will be attracted towards the nucleophile. And now the starred carbon atoms are electrophilic centers as they will have partial positive charge due to polarity of bonds. And this is because of the polarity of these bonds. These bonds become polar because of the polarization of the paired pair of electrons or the electron density that we see here. Now note that the electron rich moieties also behave as a base. So what we have seen earlier, electron rich moieties are they also behave as Lewis base. So they are actually Lewis bases as well. So nucleophiles are also Lewis bases. However, basic character and nucleophilic character do not go in parallel. So they always do not go in parallel one to that. They always, however, basic and nucleophilic character do not always go in parallel. Sometimes it go in parallel, but sometimes do not go in parallel. The basic character is primarily associated with higher electron density. So if a species is having higher electron density, one can say that this is having a higher basicity. On the other hand, nucleophilic behavior is predominantly controlled by polarizability of the electron carrying species. And the polarizability of the electron carrying species, if the species is highly polarizable, and its polarizability is high, then in that case, what will happen? The nucleophilicity will be more. And thus, within a group, the order of nucleophilicity is opposite to the order of acidity. So, what do we see as you go down in a group? Usually, the electron density will decrease because the size of the atom or the ion increases. The atom increases, and so the corresponding ion size of the corresponding ion, anion, will also increase. And so, what will happen? Then the electron density will decrease. But what happens? The nucleophilicity increases. Why nucleophilicity increases? Because with the increase in size, what happens now? The attraction of this electron pairs to the nucleus of this atom is now what it is decreases. So effective nuclear charge, it means the effective nuclear charge decreases as we go down the group, and so because of that, the polarizability increases. These things we have already seen earlier in periodic property chapter. So the basic character, what do we see? The nucleophilic behavior is predominantly controlled by polarizability of the electrons carrying the species. Polarizability increases as we go down the group, and thus within a group, order of nucleophilicity is opposite to the order of acidity, because as we go down the group, electron density of the density will decrease because the atomic size increases. And so the same charge is on the larger size, if the same charge is in a larger volume, so the electron density is lesser. And the electron density is lesser, the basic character will decrease. So for example, SH minus is a better nucleophile than OH minus ion. So SH minus, because a sulfur atom is having a negative charge and this atom is its size larger than oxygen, and so it is a better nucleophile because it is more polarizable. The sulfur atom is easily polarizable. Its polarizability is more than OH oxygen atom. This oxygen atom is having a higher electron retention tendency because of higher electronegativity or higher effective nuclear charge of this oxygen atom. But this atom is having lesser effective nuclear charge or so lesser electron retention or electron density retention tendency. So it's the attraction of nucleus on the outermost shell will decrease, and so these electrons of the outermost shell are now can be easily deformed or easily polarized towards a certain group, and so that is why its polarizability is more. But what do we see? The OH minus is a stronger base than SS minus. And why OH minus is a stronger base than SS minus? Because electron density on OH minus more, because oxygen is a smaller atom, and thus this OH minus is a smaller ion than SS minus ion, and the size of OH minus ion is smaller than H minus ion, and so OH minus ion is a stronger base. Another way to understand which one is a stronger base is to see which acid is a stronger acid. We know H2S is an is a stronger acid than H2O, and this is because another reason is that mismatch of the atomic size. Sulfur is much larger than hydrogen. We see that oxygen is also larger than hydrogen, but the disparity is not as much as we see in the case of acid, and so orbital overlap in acid decreases because of the higher disparity in the size of hydrogen and sulfur, and so this acid bond is more polarizable, and so this is what we that can easily be broken, and so SH minus is what this is. H2S is a stronger acid than H2O, and if H2S is a stronger acid, then SH minus is a weaker base, because we see the conjugate. If an acid is weak, then its conjugate base is a strong, and if an acid is a stronger acid, then its conjugate base will be weaker. So here we see H2S is a stronger acid, so its conjugate base SH minus will be a weaker base than this. So let us now see another question. So arrange the following species in increasing order of basicity and nucleophilicity. Now first example is F minus, Cl minus, Br minus and I minus. So what do we see as we go down, the group polarizability increases, and since polarizability increases down the group, so the nucleophilic character will increase that we go down the group. So these are all electron rich species there, so they all are bases as well. But what do we see? I minus is a stronger nucleophile, a strongest nucleophile among all these, and so the trend goes like this. The I minus is the strongest nucleophile, then Br minus, then Cl minus, and then F minus ion. But the basic CT order will be in the opposite order, and the F minus having a smallest size, so highest electron density means the charge divided by volume, or the charge divided by radius is highest, and so F minus is the strongest way, then Cl minus, then Br minus, then I minus, because we know the size increases in this direction. And because size increases in this direction, we see polarizability increases in this direction. And so because polarizability increases, nucleophilicity order will be in this direction. Now the next question is CH3 minus, NH2 minus, OH minus, NH minus. These all examples are from the same period. These examples are from the same group. Now these examples are from the same period, and so also these atoms, the carbon, nitrogen, oxygen, and chlorines are there in the same period, and they are adjacent to each other. So what do we see? That as we go from left to right in the periodic table, atomic size decreases. And atomic size decreases, effective nuclear charge increases. And because of that, what do we see? The polarizability will also decrease as we go from left to right in the periodic table in a period of the periodic table. And so CH3 minus is carbon based, and nitrogen, oxygen, and chlorine. So we see the carbon atom size is decreasing. That is, carbon atom is having this negative charge, and now in this species, negative charge is on the nitrogen, and this is negative charge on oxygen, and this is the negative charge is on chlorine. So the atoms which are carrying the negative charge, their size decreases in this direction, so their effective nuclear charge will increase. So polarizability will decrease, and because of the decrease in polarizability, we see the nucleophilicity order will be in this direction. So CH3 minus will be the strongest nucleophile, then NH2 minus, then OH minus, then F minus. But what we see, although the size decrease happens as we go from carbon to chlorine in a period, but what happens is decrease in size is not as much as we see the increase, or the difference in size is not as high as we see when we move down in a group. And so what happens, even the we see the basicity order also follow the same trend. So order of basicity will also be the same, like CH3 minus will be the strongest base, and CH2 minus, H minus, then F minus. So another way to understand which one is the strongest base, or which one is a stronger base among these, is to understand what is the polar nature of this bond. So HF is most polar because of the highest difference in electronegativity between hydrogen and fluorine. So if this bond is most polar, so the acidity of this HF will be the strongest acid. Then H2O bond is more polar because of higher electronegativity difference H, then comes NH2, and then comes CH3 or the CH4. Sorry, this OH2O, then NH3, then CH4. So CH4 CH bond is least polar than among all these species. So we can compare CH for the conjugate acids of these bases. So the conjugate acids of these bases are CH4, NH3, OH, and HF. In these conjugate acids of these bases, what do we see? HF is the strongest acid because of the high polarity of this bond is highest among these conjugate acids, and the polarity of the CH bond will be least among all the conjugate acids. The CH4 methane, the polarity of CH bond is least. So one can understand the order of acidity of the conjugate acids, and so order of acidity of conjugate acids will be HF, then H2O, then NH3, then CH4, and thus their corresponding bases or the conjugate bases will follow their strength of the basic character will follow opposite direction, because stronger is the acid, weaker is the conjugate base. Weaker is the acid, stronger is the conjugate base, and this acid is stronger, so its conjugate base will be weaker. This is the strongest acid, is the strongest acid, so it minus is weakest base. Hen is weakest acid, so its conjugate base will be strongest. And thus, what do we see? If we see the changes in the same period, we see the acidity and basicity, their order follow same trend. So those they go in parallel. So nucleophilicity and basicity go in parallel. Then again, the example, third example is two and ammonia. Actually, these two examples one can understand. So they are also electron differential, lone pair of electrons. Although this nitrogen is having only one lone pair of electrons and water is having two lone pair of electrons, that this ammonia is more nucleophilic than water, and the basicity order will also be in the same order. Ammonia is a stronger base than H2, although this oxygen is having two lone pair of electrons, but this oxygen is also having high electronegativity, so it will not let its lone pair of electrons go so easily, and so its basicity will also be less. And so the here what do we see? The electron, and just looking at the size, you may not understand the order of basicity in these two cases, because just by N, and oxygen is having a smaller size and it is having a two lone pair, because these species are not having a negative charge. So the electron density, you may not directly conclude the basicity in terms of the electron density, but you can conclude the basicity of in terms of the availability of the lone pair of electrons. The ammonia having nitrogen is having lesser electronegativity, and so its lone pair of electrons will be more easily available than the lone pair electrons of water. Because of water, the oxygen is having high electronegativity, and so basicity of will be this ammonia will be a stronger base than H2, and then this, and the nucleophilic order we have already seen. Note that nucleophilicity is parallel basicities among nucleophiles, where the nucleophilic atom is same. So when the nucleophilic atom is same, so nucleophilicity follow the basicity order. Order of basicity will be the same as the order of the nucleophilicity. And so again, I'll take note that the nucleophilicity is parallel basicity among nucleophiles, where the nucleophilic atom is same. When the nucleophilic atom is same, then in that case, if you have having different nucleophiles, then what happens? Nucleophilicity and basicity will go in parallel. So if the nucleophilicity increase in certain direction, in the same direction, basicity will also increase, or the same, this will nucleophilicity and basicity will also be parallel when nucleophilic atoms do not differ significantly in size. And when they do not differ significantly in size, as we have seen in this case, then we see these cases nucleophilicity and basicity follow the same order. Although we see a difference in size, but that difference in size is not very high, not very significant, and so basicity and nucleophilicity follow the same trend. In these two examples, as we see the same results. However, different nucleophiles having same nucleophilic center, nucleophilic atom, the example is this. So what do we see? Ro minus is a stronger base because the R is electron donating species, so it will increase electron density as oxygen, this Ro minus and oxygen atom of this Ro minus center, and so it will be more basic than HO minus. And so this is more basic, so it will also be more nucleophilic. And this HO minus, then again we see RCOO minus, RCO2 minus, and this RCO2 minus, we will see this electron density will be later on, we will see it will switch between two oxygen atoms. Sometimes it will be in this oxygen atom, one oxygen atom, and next time it will be on the another oxygen atom. And so because of that, what do we see? The electron density is now varying, and this electron density is now the half electron density will become minus half on one of the oxygen atom, because both the oxygen atom carry negative charge, and they actually carry effectively minus half negative charge. And so the electron density decreasing, so this RCO2 minus will be a weaker base than this. And so it will also be a weaker nucleophile than HO minus hydroxide ion. Then comes ROH, the alcohol. We see there is a minus half negative charge on each oxygen. So it is having a negative charge. So it's a negative charge is always more, the electron density in a negative charge is always more than the lone pair. So this will be a stronger base and as well as a stronger nucleophile than ROH, because this is a neutral species. Although it is having a lone pair of electrons, it can give its lone pair of electrons, so it can behave as a base. But this lone pair of, you do not see any negative charge on this center, so it is not electron excess species. This species is an electron excess species, so its electron density is larger than this species, more nucleophilic, as well as a stronger base than this. And again, if you compare these two, we see R is electron donating group, and if R is electron donating group, so it will donate electron density to oxygen. So this oxygen will be having higher electron density than this water. And this is the alcohol example is alcohol. So this alcohol is stronger base than water. And so alcohols are a stronger base than water. So they are also a stronger nucleophile than water. This is because the nucleophilic species center, the atom is same, oxygen atom in all these cases, and that is why what we see the basic order, basicity order, and nucleophilic order follow the same trend, so they go parallel. In such examples, here also they go parallel because we do not see much difference in the size of the nucleophilic atom. However, in the previous example, in this example, we see a significant difference in the size of the nucleophilic atom. So we see the basicity and nucleophilicity follow opposite trend. In this example, SH minus and OH minus, also we see the nucleophilicity and electrophilicity. They are anti-parallel, they follow opposite trend. So also basicity is determined by proton acceptor tendency of an electron rich species, whereas nucleophilicity is determined by how fast an electron rich species combines with an electron deficient center. So in this electron deficient center usually is a carbon atom, and this electron deficient proton acceptor tendency means the bases provide its electron pair to H plus ion, H plus ion is the proton, and nucleophiles provides its lone pair of electrons usually to a carbon atom. So this is another difference between nucleophiles and a base. And in fact, nucleophilicity depends on many factors, including charge, basicity, solvent, polarizability, and nature of the substituents. And the nature of substituents, how the nature of substituents affect the nucleophilicity or electrophilicity. This point we will see later on. The charge we have already seen. If the real charge species is there, it is having negative charge, it will be more nucleophilic than if it is a neutral species with a lone pair of electrons. And now lone pair electrons are more easily available than pi electron density. So lone pairs are stronger nucleophile than pi electrons. So we see a trend, the negative charge is more easily available, is more nucleophilic than the lone pair, and lone pair electrons are more easily available, more nucleophilic than the pi electron center. So these are the three electron rich centers we see in organic chemistry mostly. And then basicity, we have already seen basicity here follow certain trend nucleophilicity follow the same trend of many nucleophiles in this. Then polarizability, the example we have already seen, and the nature of the substituent and also the solvent. And usually what happens, nucleophilicity is decreased by hydrogen bonding of polar protic solvent, and the protic solvent examples are water and alcohol. These are polar solvents and they are also protic solvents because they can provide H plus electrons. So they H plus, sorry, protons. So they can provide protons because they have polar OH or OH bond. The alcohols or water, even liquid ammonia is a polar solvent, polar protic solvent. So these are solvents which can provide H plus ion to an electron. Rich species so nucleophiles usually are electron rich, and so they are electron rich, so they are also bases. And when they are bases, they also behave as bases, and they can abstract H plus ion from the protic solvent. So nucleophilicity will decrease because of this. Because they can abstract H plus ion from the protic solvent. The protic solvent is a solvent which can provide H plus ion proton, and thus the nucleophilicity decreases in polar protic solvent. I'll stop this lecture here, and then from the next lecture we'll see electron movement in organic reactions and some kind of effects we'll be studying in our next lecture.